All right, guys. So yesterday I had somebody drop by office hours, and we got talking about what the first principles does, and things like that, and how there's a very tedious process, and there must be a better way, and there is. That's what we're going to spend our time doing this week, right? And I was reminded of um, this. This is not much different from when you guys did factoring in grade 10. You'll recall that there were, 6 or 7 different kinds of factoring for different scenarios, right? Um, and sometimes, like, you could combine factoring styles, right, to ultimately fully simplify the expression. That's not entirely different from what we're going to see this week in that we're going to be posed a bunch of different situations with functions, right? For instance, today's is what happens when we multiply two functions together. How do I find the derivative when I multiply two functions together, right? Um, and so that's what we're going to spend our time on today. Yesterday we saw the simplest form of a derivative, and that was the power law. We're going to apply that to um, the product rule. We're going to need to use that in product rule. There's just a little bit more with product rule. Okay, so first things first, I want to show you guys that intuitively one might think, if I have this function, this new function, h of x is the product of f of x and g of x, then why couldn't I, in theory, like the derivative of h of x would be the derivative of f of x multiplied by g of x? Well, intuitively that makes sense, but let's take example 1 here and show that that's not actually true. Okay, so let's one thing we could do, and you don't necessarily want to do it because we can have more. There's no saying that we can't have a function h of x is equal to f of x times g of x times z of x, right? And so on. We could have an infinite number of these things, right? Um, and so imagine having to multiply or expand these all out all the time just to find the derivative. That's also a laborious task, right? So why don't we? Well, you can do it. So we'll say, okay, well, h of x is telling me that I'm going to take these two functions, f of x, right? And I'm going to multiply it against g of x. So I'm going to say 2x minus 3, that's f of x here. And I want to multiply that against x plus 1. So I'm going to expand that, and I'm going to get 2x squared minus 2 plus 2x plus 2x minus 3x minus 3. And that's going to be 2x squared minus x minus 3. Now, that's h of x. H prime of x, you guys would have learned yesterday, we could apply our power rule to this, right? And we're going to say, okay, well, I'm just going to derive this. So it's going to get 4x minus 1 will be the derivative here, right? I got that by taking the exponent and multiplying it by the coefficient and subtracting 1. We saw that big long proof yesterday. And same thing here, this is the exponent on that is 1. Now, this is the actual derivative. This is the answer. What I want to do here is show you that this is not true, right? So h prime of x, if we're testing this theory, we want to say that this does not equal f prime of x times g prime of x. Well, let's check this. So it shouldn't equal, well, if we take the derivative of f of x, that's just 2. And the derivative of g of x would just be 1, right? Oh, I guess I don't need that, right? And so we get 2. Well, these two things don't match, right? And so this is the proof that this does not work. Okay, so it's okay to expand and then apply your power law, I suppose. But just know we are going to do something at the end of this lesson that, like, you're not going to want to expand this stuff and apply power rule. Let's just get longer and longer. Okay, so here is actually the formal definition. So if we have a function h of x, this new one, where we've multiplied two functions together, f of x and g of x, then the derivative this is the piece that you want. The derivative is going to be equal to the derivative of the first one, f of x, so f prime of x multiplied by g prime of x, multiplied by g of x, the original g function. And then we add on, we derive the g of x function, and then we multiply by the original f. Okay, and so sometimes it helps, you know, if you want to label this one f of x and this one g of x, and underneath you want to say, okay, well, dy dx, remember this is just a different notation. We're deriving y with respect to x. That's what that reads. We can say, okay, well, I want f prime of x multiplied by g of x plus f of x multiplied by g prime of x. Okay? And so all you have to do is say, okay, well, I'm going to derive f of x, right? Well, the derivative there is going to be 2x plus 3. And I'm going to multiply by the original g of x, so 2x plus 7. Plus, we could say, okay, well, f of x, the original f of x function is x squared plus 3x minus 1. And multiply that against g prime of x. Well, that's going to be 2. So we can do the expansion work now. We're going to say 4x squared plus 14x plus 6x plus 21 plus 2x squared plus 6x minus 2. Okay, clean up all the terms. You should see 6x squared. We're going to have 14, 6, and 6, so 14 and 12 should make 26x, and 21 minus 2 should be plus 19. Okay, that would be the derivative dy dx, right? Okay, then we can do the next one. Oh, we got two functions here. We have t of 4 and 2t minus t3, right? So we can say, okay, well, s prime of t, that's going to be the derivative of the first one, so 4t cubed multiplied by 2t minus t cubed. And then we need to add we're going to derive the original function multiplied by the derivative of the second one, right? So we're going to see that it's negative 3t squared plus 2. Okay, and then we can do the expansion. We're going to get 8t4 minus 4t to 6 plus minus, because of the minus that's in here, minus 3t6 plus 2t4. Okay, then we can clean this up. S prime of t is equal to 8 and 2. We can combine, and then we can combine these two here. So we can say, okay, well, we get minus 7t6 plus 10t4. Okay, that's it. That's your derivative, f prime of t. Okay, so what about if we start mixing in the questions where we have to actually, like, we're interested in the slope of the tangent at one particular x value. This does not change, right? The question does not change, right? All we're doing is we're applying our product rule and then evaluating, right, what the slope actually is when x equals 1, right? So let's find the derivative, right, dy dx, and then evaluate where x equals -1, and that's going to tell us what the actual numerical slope value is when x equals 1 relative to this function, right? So we're going to say, okay, well, dy dx is going to equal the derivative of the first one, f of x, right? Or you could call this f of x. I don't know. Sometimes if you guys are doing this for the first time, it helps, right? And I think I remember doing this when I was doing this for the first time too. And as we get more complicated questions, it's going to help you to write down product rule every single time that you do a question. It'll lock itself in there, and then you won't need it anymore, right? Hopefully by the time the summative rolls around and by the time you've done questions today, you know, if you wrote down the product rule every single time, right, you might not need to write it down anymore, okay? So it's a good reminder of, okay, well, I'm going to derive f first, multiply it by the original g, and then add the derivative of the g multiplied by f. Okay, so dy by dx is going to equal f prime of x. We're going to get negative 12x squared, right? And then we're going to multiply that against 2x plus x squared. And then we're going to add g prime of x is going to be 2x plus 2, and multiply that against the original f function. Okay, and now we can expand this and clean it up. We have 2 more lines here, right? So we're going to expand. We're going to get negative 24x cubed, and then negative 12x to the power 4 plus 6x minus 8x4 plus 6 minus 8x cubed. Okay, and then we can clean this all up. So dy by dx is going to equal negative 12x4. And what I try to do all the time, again, is just I try to write things in descending order all the time. I don't know if it's, I think it's just maybe good practice. Descending order being highest powers come first. So negative 20x to the power of 4, negative 24 minus 8x cubed, negative 24x cubed minus 8x cubed would be negative 32x cubed plus 6x plus 6, if I'm not mistaken. Okay, and now that we have this, we can evaluate when x equals 1, right? X equals negative 1, sorry. So we could say, well, what happens when x equals negative 1? Well, we're going to say negative 20. The actual slope is going to equal negative 20 times negative 1 to the power of 4 minus 32 to the negative 1 cubed plus 6 times negative 1 plus 6. And if you do the math on that, you should see that dy dx, or the slope, is equal to 12. Okay. It's not too bad. It's the same work over and over again, right? In terms of the process, if you look at the big picture of these questions, when I'm provided an x value, I'm looking for the specific slope at that x value, right? Well, that answer is 12. The slope when x equals negative 1 is 12 for this question. Okay, it's the same work we were doing before, right? With the exception, you know, we're just applying a derivative law now, right? That's much nicer to use than first principles, for sure.